Hello, everyone, and welcome to today's panel discussion. We're going to explore topics in the field of clean tech and energy storage. We're going to start with some brief introductions and then about a 45-minute panel discussion, and then afterwards we'll open it up to questions from the audience. Next. So my colleague Keith Wood and I are both with Hamilton Brook Smith Reynolds. Keith, you want to introduce yourself?
Sure thing. So can everybody hear me okay? All right, great. So yeah, I'm Keith Wood. I am a patent attorney, counsel at Hamilton Brook Smith Reynolds. I have over 25 years of experience. My background is in physics, and my practice focuses on patent prosecution and contested matters such as administrative trials at the Patent Trial and Appeal Board. So it's great to be here tonight to be moderating this panel.
And I'm Ron Dempscher. I'm a principal attorney at Hamilton Brook Smith Reynolds. I've been working in IP law for about 30 years. I've been with Hamilton Brook Smith Reynolds for just over 11 years. My technical background is electrical engineering. I've worked in industry for about 13 years before I decided to switch careers and go to law school. During that time, I was first started working in digital signal processing and ended up working in RF and the front ends of radio systems, of communication systems. Next slide. So Hamilton Brook Smith Reynolds is a law firm with a history of over 40 years. We have an office in the Seaport District down in Boston, and we also have an office in Lincoln, Massachusetts, near Hanscom Field. HBSR employs over 70 people, about 30 of which are attorneys. Our practitioners have a wide range of tech backgrounds, which enables us to handle an extensive catalog of technologies. Next slide. Two of those IP technologies are clean tech and energy storage. Clean tech is generally directed to technologies for reducing adverse environmental impacts. Energy storage techniques dovetail with clean tech, for example, by storing surplus energy that would otherwise be wasted. Energy storage is a fascinating field because there are so many diverse modes of energy storage that it makes it interesting. It's not sort of focused in one area. There are a lot of diverse modes. At Hamilton Brook, we work with inventors and companies to identify, assess, and protect energy storage innovations. We do that through patent acquisition and, if necessary, through enforcement of patent rights. Next slide. Now we'd like to have each of the panelists briefly introduce themselves. Michael, would you get us started?
Sure. I'm Michael Huff. I'm the CTO at American Energy Storage Innovations, and I'm primarily involved with looking at new technologies, particularly in the battery space, but I also work with Ron on patents and at our company.
Good evening. So I'm Nicolas Chanu, and I'm a research scientist at the KU Leuven in Belgium. And I've been working for a few years at MIT on energy storage systems, so where we also have a few patents going on with HBSR.
Good evening. I'd like to thank HBSR for the invitation to come here. My name is Christopher Benkel. Quick background, I was a former Navy pilot and flew for 24 years, TAC helicopters. And then when I retired, I went to Raytheon, and I was the business executive for advanced tech programs there. The last time I was here, I spoke in front of a large group of people, and it was a really, really fun experience. So collaboration is key. I thank you all for coming out this evening. I am currently the president of WL French Hydropower Holdings, and we do business as FD Hydro. So what that means, I'll be explaining in a little bit, but it's a pleasure to be here tonight. Thank you. Hey, it's my stuff.
Okay, great. Thank you, all three. To start off with, if we could go back to Michael Hoff's slide, I just want to ask each of the panelists in succession. We're going to start with Michael to discuss the background of the technology that you are most closely involved with at your company. So if we could go back to that slide with Michael Hoff, that'd be great.
So this is a picture of our product. We're releasing it this quarter, and I'm using it to highlight some of the things that not only we've innovated on, but the industry has moved forward with. The first thing is cells have gotten a lot more energy dense over the past few years. Even in our development program, our 3-year development program, they've improved their energy density by 15%. So we went from 7 megawatt hours in this box to 8 megawatt hours. The other thing that has been happening in the industry is companies are finding their own custom enclosures. 15 years ago, when we started in this business, our first customer came to us and said, hey, can you build this battery in a 53-foot container? And we said, what the heck for? We had no idea what this energy storage thing was about. But we've been using 40-footers, and the industry has been 40-footers, and now there seems to be a convergence around 20-footers, but even that is going to be hard to handle. A lot of companies are innovating on making their own custom enclosures, and what that does is it makes the site density very efficient from an energy standpoint. Also, what they've been doing is you've heard this in the automotive world, this thing called cell to pack. And in the beginning, we used to make modules, and then we put the modules in the rack, and then we put the racks in the container, and then we put the containers next to each other. And it was a lot of assembly. There's extra steel that you don't need. Now, we just line up a bunch of cells in a very lightweight package, and we put them on shelves in the box, and that's what we call cell to pack structure. Now, all of that, the energy density, the packing density, leads one to think, well, is this dangerous, having all this energy in a spot? So one thing that we've been working on is this thing called zero cell-to-cell propagation. In other words, if anything happens in one of these cells, it doesn't propagate to the other cells. And if you know anything about batteries, when a cell goes into thermal runaway, you're not putting it out. It's going to use up the fuel inside it, and then it's going to go out when its fuel is used up. So you got to keep the other cells from getting into thermal runaway. If you don't, then you got a mass conflagration. And then along comes it, and you're thinking, well, why is he working with such dangerous things? Well, if you put 1 million cells out in the field, and there's 1 in a million chance that a cell's going to go bad, guess what? It's going to happen. So you have to design for it, right? Even though it's a rare occurrence, you still have to design for it because you want to keep people safe. So when cell does fail in those rare cases, there's going to be gas. So not only do you have a fire and thermal event, but you'll have smoke and gas detection. So there's been companies out there sniffing the right flavor of gas that comes from the cells to make sure that you can detect it in time and maybe do something to prevent it from getting worse. And the other things that we've been innovating on is we have to install a lot of energy storage in the planet to make ourselves decarbonated. I'll talk a little bit about that later. But you're not going to do it by working on the site with a whole bunch of EPC effort. So what we did is we put the cooling inside the box, we put aux power in the box, we put the PCS power controls in the box, we put the site controls in the box. Everything's in the box. All you have to do is drop it on the site. 6 hours later, you can start commissioning. That's what we bring to the industry to make it easy to install. Chris is actually going to talk about easy to install from another technology too. It's a trend. We have a lot of energy storage to put out there, and you're not going to do it with these 3-year-long projects that we've been used to for the past couple of years. So the other thing that we've been doing, we have this little trick. If you know anything about batteries, a lot of times they'll make a series string, a series string, a series string, and they'll put them all in parallel, and they'll run them like that. Well, we decided, let's get rid of that. Let's just put them all in parallel first, and then put them in series. There's some very subtle benefits to doing that. And first thing is you can make all the cells work together in that one module. When they work together, they deliver all of their energy, or most of their energy, as opposed to when they're in series, the weakest one wins or loses. So that's our little trick that we bring to the energy storage. But anyway, I'll take questions later, but we'll give it to Nicholas.
Okay, thank you, Michael. And incidentally, we will be having questions at the end of the program, so we'll be looking forward to that. So now, Nicola, if you could tell us a little bit about the technology that you are most closely involved with in your research.
Yeah, definitely. So maybe just a little bit about myself first. So I told you I'm now a research scientist at the KU Leuven, so where we are developing some methodologies to study the diffusion into porous materials. So we do that to try to understand how fast ions are going to diffuse into a material, just to understand how fast we can store energy. So we are working basically to characterize supercapacitors. And this is the technology that we started developing when I was at MIT for the last 5 years, and I'm going to talk about today. So what we did, I come from a civil engineering department here at MIT, and we wanted to introduce some electrical property to the cement. And because why cement is an extremely cheap material, it's everywhere. So this is what we decided to do. We took cement and we added some extremely cheap materials to it. So carbon, something that can be sourced virtually anywhere and potentially at a low price, because if you start working with concrete or cement, you need low prices to be able to do to work into this industry. And so the idea, as you can see, is that we had simply the cement carbon aggregate. So in a very simple way, we create this percolated network of carbon into the cement. So a percolated network will basically be a wiring inside the cement that will be used to conduct electricity through the material. So through that, we can give new functionalities to the concrete. So being self-heating. So for example, when you just pass a current through, the sample is going to heat. So we use it for de-icing, for example, de-icing of sidewalks, of roads, because a lot of issues come from freezing. When you freeze on a road, you're going to create some cracks in there, and it costs you a lot of money to redo that. So maybe sometimes just a simple thin layer and heating could help just avoiding this kind of impacts. The other thing we are doing with that is we are making electrodes. So instead of just having a block that's heating, we can use this as an electrode for a supercapacitor. So the idea here is to store energy inside the concrete. So it's kind of the supercapacitors are known to have low energy density. So that's one of the big drawbacks they have against batteries, for example. And here our idea behind is to use this large volume, unused volume in the construction industry. So here we can compensate this low energy density into these materials by you leveraging, let's say, all this volume that's there and doing it in a cheap way, adding like carbon black, for example, is $1,000 a ton. Concrete would be $100 a ton. If you had 10% of that, you double the price of your concrete. So it's a lot in the concrete industry, but you introduce all these functionalities into that. So this is basically what we did. The concrete in itself has these mechanical properties. So the matrix in itself bring a structural integrity of the structure, and by the carbon we can use basically store the energy in there. So this is what you see here, and you can see the prototypes. So we are at a research level, so we don't have a product yet. We are working in developing all these technologies. We have a few patents on that, and what you can see here is our first prototype. So we can store energy, light up things in there, and all this research led to a newly established hub, so the MIT C3 Cube hub. So it's electron conducting cement carbon hub. So that's funded by Aizawa Corporation, so in Japan. So it's a multi-year project, a research project that we established with them. And yeah, with the idea of behind to go in everything that's structural. So structural energy storage systems, so from houses, renewables, even using capacitors. We are working on some system for on-road charging of the cars, for example, by pulsing energy for induction system, all this kind of ideas.
Okay, thank you, Nicola. And Christopher, you could tell us about the technology.
Thank you. So there's a reason why I'm sitting next to this man. All right, so I kind of told you my background before was super high-tech S&T, DARPA, AFRL, Office of Naval Research, and doing that, right? And then I realized working that part of the national security domain that what we have a lacking for, and soon to have a greater lacking for, is available power. So my world as a Navy pilot, and I will confirm that a battery fire thermal runaway, the emergency procedure in the aircraft is to land immediately. Because if you don't, the nose of the aircraft will blow off and you will have a bad day. So that's really important. What you're doing, we are going to be talking because we're looking for advantage. So now I want to engage you all. Please give me a show of hands, and don't be embarrassed or anything. We're all friends here, okay? How many people are familiar with pump storage hydropower? That's much more than what I normally see, okay? Now, how many people, I assume that most of us live in the area. I was born and raised here. How many people are familiar with a place called the Mountain or Northfield Mountain, right? So what Northfield Mountain is, and it'll explain kind of these images, these simple graphics that I have up there. Northfield Mountain out near Springfield in Northfield, Massachusetts, houses the 1,250 pump storage hydro facility. It's an open loop system, which sometimes gets bad press because when you have a 30-foot diameter tunnel of water racing down a 1,000-foot drop, it hits that river really hard. And the sediment and the disturbance to the ecological environment, I'm not poo-pooing it. I know Justin, the CEO at First Light, very well. But when I first got a chance to go a half a mile underground and see the facility that saves the grid when the grid gets like this in the Northeast. And most people don't know what that is. So what you see here, it's very simplistic drawings. Thank you, Department of Energy, for providing them to me. On the left, you'll see basically an open loop system. All you have to think about open loop wise is it comes back into the environment, so it's flowing, right? So you'll have an upper reservoir, and then it'll come down into the river. That's an open loop system. There are 39 pump storage hydro facilities in the United States right now that encompass 23 gigawatts, that's gigawatts of power, stored long duration energy storage. To the tune of 96% of our country's, and no offense, right? I'm not here to offend battery storage or one's better, we need everything. But 96% of our country's long duration energy storage is provided through the water battery pump storage hydropower. We haven't built one in over 25 years. On the right image, what you're seeing is that's a closed loop system, less intrusive to the environment. When you start talking 1,000 megawatt systems, these are in the area of $3 to $4 billion to construct. Sorry, I have to move around. I'm just itchy as a pilot. What I have here, and we're going to talk about this later, is the value proposition of what our company, working with modular precast, brings to the hydro industry. In just a couple more minutes, W.L. French, or Bill French Sr., the founder of our company, You've seen his trucks drive around Boston all the time. They move Boston, okay? Created a tremendous civil construction company, one of the best in the entire Northeast. He then decided to do something else with his time. So we started buying all the patents for the hydro industry, hydropower, dams, aquatic animal fishways, pump storage hydro. We just got the patent approved. Thank you, Mark. December 31st of 2024, we now own the patent for precast system for pump storage hydro. The value, and I'm all about creating better turbines, variable vane turbines, all that stuff's important, but from a business perspective, where do you make the impact? The impact is in using precast, and I'm kind of sharing everything with you now, but we were under contract on a real project to evaluate a $4 billion project, I'll just say out west in the United States. And the value of doing a precast manufacturing facility on site, no transportation costs of these modules that sometimes weigh 60,000 pounds to 80,000 pounds. You can build them on site as long as you have the materials that you need. So the transportation goes out. While you're excavating a $4 billion site, which is quite large, you're manufacturing in the USA precast modules that are sequenced, placed, and ready to go to construct. In 2010, Bill French, along with a company called JF White, did a program called the Fast 14. Most of y'all live here. Most of you used to 93 traffic, right? When you leave, there are 14 bridges and overpasses starting in Medford first, going up 93 to the New Hampshire line. Bill French and JF White was the prime contractor. Bill used his fleet of Kenworth vehicles to move the precast modules onto site. 2 bids. One bid came in at a 3-year period of performance on the bid, working single lane traffic in and out of Boston on 93. You'd be going up to Montreal to make the U-turn to come into work. We all know, right? Bill and JF White came in and used precast methods and means and introduced it to the Department of Transportation in the 2009-2010 timeframe. And they did them all on the weekends and completed it in 18 weeks. 3 years, 18 weeks. Set the standard in the entire United States, everything going on in California and everything in between. All the bridges and overpasses are done with precast. Cuomo Bridge, formerly known as Tappan Zee before they tore that one down and put Cuomo up, it's all precast. It's precast sections, right? Football stadiums, precast. Cities like Abu Dhabi and Dubai, where I've spent a lot of time, precast, right? So aged infrastructure, which we have in this country, needs to be addressed. High hazard dams, if they're no good, tear them out. If there's no viable power, source power that can be extracted, consider it. But, you know, whenever you do something like that, especially in the Northeast, everybody knows the mills. Everybody knows the bad dirt behind the mills. Bill French, #1, waste management, soil remediation guy in the entire Northeast. He knows, right? We have to do it the smart way and the right way. Our patent portfolio is extensive. And I want to save this one just to talk about, because I want to talk about that one case study of how much money we actually saved by shaving a year off of a construction plan. It's hard to read. The civil works portion of pump storage hydro is approximately 67 to 70% of cost. If you shave a year off of that, there's tremendous value. That's the value of proposition of what we bring to the table, okay? But we do everything together. Cutting edge sensors, obviously teamed with smaller to medium pump storage, the larger pump storage coupled with the batteries, it's an all hands effort. The new administration, like them or don't, Chris Wright is going to do an order. They're going to develop source power, right? There's a lot of discussions about counter wind, counter nothing. We got a shortage. And if we build data centers with millions of server farms, it's going to create a serious stick going up with the power required. So as a pilot, it's all about power required versus power available. And so sorry I went on a little bit long and kind of explained that, but I will get into more details of the value. The biggest thing is, and I'll speak for all of us if you don't mind, you've met us now. Don't be shy. You got a question. Hey, I had a question on what you said, and communicate. I'll leave all my business cards over there. Please take one, right? I'd be offended if you didn't, and I'll be offended if you don't get in touch with me about something, okay? So anyway, I'm going to hand the mic back.
All right,
thank you.
Thank you, Christopher. So we're going to go back to Michael. Just big picture question here. Why is energy storage important for the renewable industry and for decarbonizing the grid?
As a softball, Keith, thank you. So, food is stored. Energy is stored. We have big warehouses, tanks underground and tanks above ground. We've been doing this since we left the garden. And believe it or not, electricity can be stored, but you have to turn it into some other form, like chemical or gravitational or something like that. Our present electrical grid has stored energy in terms of fuel. So we put the fuel into the plants when we need it, and the load, if you look at the graph of a load usage on a daily basis, it goes up and down, sometimes 2 to 1x on a daily basis. But renewable energy doesn't follow our human habits. It shines when the sun shines, and the wind blows when the wind blows. So we have to move it from the time that it's available to the time that we need it. And like, for example, in California, the prices almost go negative every single day because there's so much solar in that state. And then when everybody gets home and plugs in their Teslas and fires up their ranges, their electric ranges and air conditioning, the sun has gone down. So you got to move all that energy from one place to the other. So in California, the peak summer demand is about 40 gigawatts. And if you removed all oil and gas generation from that mix, you would need to move 230 gigawatt hours of energy from one time of the day to the other just to keep the lights on. So if you do the math, that's about 6x the peak summer load. 6x, just remember 6. This session is brought to you by the number 6. And so if you project that out to the US is projected to be about 1.1 terawatts worth of peak summer load. And I say summer now, winter's going to be the worst one in the future year. But if you multiply 6 by 1.1, you get about 6 terawatt hours. So we have to install in the United States 6 terawatt hours, and that's just for the daily usage, to move it from one time of the day to the other. Now, if we were set about to do that, 6 terawatt hours divided by each year, that's 200 gigawatt hours per year. And last year, we were proud to say we did 25. So we've got a long way to go in the next 30 years. That means we have to install a gigawatt hour worth of energy storage every other day for the next 30 years. That is a big effort. And we have to start now from ground zero and start ramping up. So we're going to have to be doing a lot. Now, typically a gigawatt hour of battery energy storage would take about 3 years in today's project size. So we have to do a lot to speed that effort up. The other thing that energy storage has to contribute to decarbonize the grid is to be efficient. You can have an inefficient energy storage medium, and yes, the energy is free during the day in some areas, but it costs money to make it free. So it's really not free. So in fact, I did some quick math here. Just to move 6 terawatt hours of energy from one time of the day to the next, you would need 8 nuclear plants running full bore to power just those losses. So if you can improve your metrics by a couple percent, then you could save nuclear plants worth of energy going gangbusters all day long. So efficiency does matter. My son commented today, he says, well, Dad, if we don't decarbonize the planet, it will do it for us when we run out of oil. So we better get moving.
All right, thank you, Michael. So that's one aspect of energy storage. Yet another type of problem, we can move over to Nicola, is thinking about materials. So Nicola, materials play a critical role in enhancing the efficiency of energy storage systems, like batteries and supercapacitors and thermal storage technologies. But what are the biggest challenges in academia and industry in developing new materials, and what strategies could help us to accelerate progress in materials?
Yeah, so Michael told us of how much energy we need, but we need different types of technologies to do that. We need to basically things that can store on a shorter term, on a longer term. We talked about supercapacitors, so in the millisecond to the minute range, you also need that on the grid. You have this type of fluctuation when large load or generations, individual load or generation go on and off the grid. So you need also to regulate this AC regulation, the AC current, for example. So frequency regulation, voltage stabilization. So it's one case with the supercapacitors. It's also when we discussed about the batteries and all the other technology that's needed here. I think we have at least 3 technologies that are shown, and indeed there's materials that are needed in all of them. But one of the biggest, in my opinion at least, in the research, what's happening today is the trade-off in between energy density in all these technologies and the power density. So what's the challenge in terms of materials today and in terms of technology is to enhance or increase this trade-off, improve this trade-off into that. So the materials that are developed today, the problem of doing that is that there's a lot of combination possible into the different materials you're going to use. So there's a lot, of course, of AI attract a lot of attention now to do that onto materials, and there's a lot of large-scale computational screening that's done onto these materials, so we can basically find interesting materials early on and produce them, synthesize them later. There are different companies doing that, like in the energy storage system, energy storage, but not only, like for CO2 capture, for many materials. For example, Newmat is a company we are working with who are basically in silico developing materials on computers and synthesizing them. So here you have you are speeding up a lot the finding of new materials. But this is one aspect of it, but I think it's not sufficient in itself because AI is still a tool. It can help us accelerate when we have a large set of data, but there's also a need for understanding these properties. So typical batteries, what's the mode of failure? So what's the mechanisms? How is it working in operation? So in situ techniques have been developed a lot, like Claire Gray was at MIT a few weeks ago, actually. They do beautiful work on using nuclear magnetic resonance to study batteries in operation, and other groups in Stanford, Quiz group, for example, is working on cryo-electron microscopy, so they can post-mortem, let's say, check what was the mode of failure of this battery. So obviously this information is critical to constrain your AI models and basically have a better understanding to make the right choices to develop your materials and speeding up the process.
Okay, great. Thank you. So a little bit of need for humans yet. Okay, back to Christopher Bankel. Let's talk about the sort of the overall picture of energy shortfalls that might occur. So how do you view the current energy shortfalls that we anticipate in the United States, and how would you recommend the strategy for the road ahead?
So it has to be we had a tendency to throw stuff on a wall and try and solve solutions. I never saw a clear, and it's no offense to Department of Energy, but I never saw a clear strategy, right? And I know that budgets, typically run out, a fiscal year development plan runs out about 6 years. And it's hard to do the outlook, like, what do we want to be 15 to 20 years from now without funding? How does it get held? Administrations change. How do we stick on that path that we're on, right? There's goods and bads to both sides. That's kind of an important thing. There are shortfalls in source power. We're all reading about it all the time, and that's important. The focus here for me is more on the storage piece, right? So I think a coordinated plan. I had a discussion with probably the leading pump storage hydro person in the country. His name is Bo. I can't pronounce his last name. It's hard, sorry. But he's absolutely brilliant. He works for a company called Mesa and incredibly talented. Anything you see with pump storage hydro will have his name attached because they trust what he has to say. And we sat at a table out in Portland, Oregon about a month ago. And I'm asking him, what's going on? Why aren't we building any of this stuff? It has to be built. What's going on? He goes, in due time, in due time. So one of the issues with pump storage hydro, well, let me start off with another thing real quick. One of the issues that I think is holding us up a little bit, and I hate to bring this up because everybody talks about it, the valley of death, right? How do you transition brilliant technologies that are developed under contract and then have the courage to transition those to, lack of a better term, the fleet, okay? In this case, every single thing in infrastructure, roads, bridges, buildings, stadiums, the World Trade Center, I mean, everything is shifting to modular methods and means. What's holding up the hydro industry from being able to do that? That's kind of a pet peeve, and we're working hard at trying to help people understand that. The other thing in the storage piece, and you had to throw out numbers, now I have to throw out some numbers, right? So currently, in the project plan in the United States for pump storage hydro, there are 96 projects. That was briefed yesterday. So that number's good. 96 projects in the queue, but they're at the early permitting stage, maybe 3 or 4 are at the licensing stage. It takes too long. The timelines are too long. And it's not a cut against organizations like FERC. They're responsible for safety. They want it built right. I understand that, but it's taken too long, right? There's no reason why a pump storage hydro closed loop system at an old worn out mine facility cannot be turned around with very, very little environmental intrusion and be powered up. Ride Development for you all is doing a project like that now at a mine in Kentucky. And they passed that thing, and Department of Energy gave them $80 million to keep moving forward. So that could be good. But there are certain numbers that need to be gotten to. Pump storage hydro, there's always a complaint about pumping uphill head, right? You got to get the water after you release it through the turbines in the powerhouse. You got to pump it back up. Your loss of efficiency is between 20 and 22%. We need to make improvements there. In my strange Navy mind, I'm like, well, why don't we put a small SNR with one line that now I have the ever functioning water battery going on in close proximity to a small nuclear reactor. Maybe that works. Maybe capacitance works at being able to accelerate water uphill. Maybe I'm not dealing with water. Maybe I'm dealing with different fluids, right? Heavier fluids to get more bang out of the buck and generate more power coming out of the thing. So there's a lot of pieces that come into play, but it's all about blend and balance. Blend and balance and time, right? Source power, we got a problem. We've talked to PJM, we've talked, and I'm not just signaling them out, these are power companies. Energy New England. This was crazy. We had the head of California ISO, that's an important person. 2 weeks before he said the situation was dire in California with power, we're on a call and he says the situation is dire. If somebody came to me and said, you know, situation's dire, that's really bad, right? So how do we fix and remedy those problems? And that's what we're focused on. Adoption of new technologies that WPTO gave us $2 million to develop the French dam. It's in Billerica right now. 6 modules. Oldcastle was the precast company. I was an exec with Raytheon at the time, so I was looking at potentially doing islanding power in a certain theater. I needed to have power because everything's about power. And driving rain, 37 degrees, sleet, one of those days you're like, oh, this is nasty. What am I doing out here, you know? And construction guys, untrained crew, place 6 modules with linkage, with, I call it the anaconda, that's the water seal. It's like this, and it's expandable water seal, double redundancy. Assembled it in 3.5 hours. Wow. Again, we control time, right? 3.5 hours, and then left it alone and no leaks after a year. So we proved the concept out. We want to get to monolithic structure. That's important, right? So anyway, power's a problem. We got to fix it. Storage is a problem. We got to fix it, but we got to fix it on a cohesive strategic path. I sure hope that the folks in Washington that are in there now can figure that out and can develop a clear, coherent strategy for the next 30 to 40 years that we'll stick to be able to get renewables off of fossils, you know, maybe SNRs, hydrogen, and other factors that are better for the carbon footprint of our world. So that's it for me.
All right, yeah, thank you. So, coming back to Michael, just from the point of view of your company, do you see room to innovate further in your company and from your perspective in the industry? So do you see room to innovate further in your own company? Where's the next step for you?
Well, first I want to follow up with that how to get to energy, how to meet the energy needs, and your theme of quick installation resonates with us quite a bit. So we got the 6-hour installation time. So do we have room to innovate? Yeah, we'll make 6 hours down to 3 hours, and there's as the energy storage increases, so we're seeing now energy, our cells increase 15%. There's another 15% on the horizon. We keep making our boxes more energy dense by doing that. We want to get down to 0 fires and 0 propagation, and so you know, I'd like to pass the meteor test. And that's where I program a meteor to strike my battery and nothing happens. Wouldn't that be nice? Because even though the chances are low, the severity is high. So that's what we're working with. And we're working with safety agencies and everything on that front. So energy density, more energy in the box, easier to install, 6 hours down to 3 hours. So yeah, there's room there.
Okay, great. Turning to Nicola, you're in research. you referred earlier to the gap between research and industry. So, what are the barriers between academic research and making ideas into economical products that that consumers can, commercial products, and how do you bridge that gap?
Yeah, indeed, and that's actually a very good question. We are working on it now, also through trying to bring our technologies directly to the industry. And I would say, there's different aspects that can be problematic. The first one is a lack that we found out, a lack of metric. So having good metrics that are proposed in academia. So basically, we are doing experiments, even us, and we have been performing a lot of experiments in an ideal environment. So when you're bringing it out, we were discussing a bit earlier, for example, you might have like problems, like civil engineering problem, and you're placing your system. So our case is just perfect. And so when you try to take one technology and bring it directly to use, you generally find some issues there. So here, this is one of the first problem. The second is that generally a lot of research groups are looking at electrochemical performance. For example, when we are talking batteries, we're talking supercapacitors, we are looking at energy density, or we are looking at a power density problem, and overlooking a lot of things that are important in the industry. So safety, costs of the material that are used, availability, is it possible to have fabrication made at scale, and so on. So I think that one of the biggest issue there is that there's these two sides, academia and industry, don't have especially the same goal initially. So we are looking maybe in research somewhere is a commercialization. But like now, today, as you said, I think there's a need to move faster into this. So I think that academia on the side should start thinking earlier into what's good for commercialization. Sometimes on the other side, that industry is ready also to jump a bit earlier and fund academic projects a bit earlier. So a step of everyone into that direction would be probably a good thing. And for example, for us, the hub that has been created, the electron conducting cement carbon hub with this Aizawa Corporation in Japan, for us is great, because we know what they are looking for, what type of products they want to develop. We start working on that. We can test also our technology, so we can de-risk our own technology by testing it in real conditions. So I think that earlier partnership in between industry and academia would be a great step to move faster to find solutions to the problem we're facing now.
So tell us, if you could tell us a little bit about, you've talked about the United States, but can you tell us a little bit about the global, maybe the global and the U.S. markets for hydropower, and in particular pumped storage hydropower?
China, I'm not comparing, but China's taking a hard turn on dam construction on the Yangtze River and in pump storage. So if you look at the amount of projects, and they're by a factor of 4 greater than what we're doing. They use the pump storage hydropower. They just, 6 months ago maybe, they didn't start, they finished a 3,500 megawatt, it's the largest in the world, pump storage hydro program. In their queue, in their business pipeline queue, sometimes you can believe what you can read. 80 to 90 of the top 100 pump storage hydro projects in the world, 80 to 90 is in China. So they understand the value of photovoltaic, wind, renewable energy, but they understand that those need to have energy, long duration energy storage, as well as other, long duration energy storage technologies underneath them. So they've taken a hard turn. We, on the other hand, are surviving on an aged infrastructure of pump storage hydro facilities. By the way, these last for 100 years. So the service life of pump storage hydro facility when we build it is like 100 years. So that's pretty impressive in itself. And I would encourage everybody, if you get a chance, because they're not considered national assets, but they are controlled, access controlled to see them in action. But if you get a chance to go out there, you go, whoa, this is pretty impressive. And the pristine nature of the ecological surroundings that First Light does, I praised their CEO. I went up and said, this is amazing. I mean, it's beautiful up here, right? Anyway, that's just in Massachusetts. So I think that it is absolutely critical. There is stuff going on in Europe right now. The UK, you can read the press. They're doing some pump storage hydro. There's pump storage hydro in Germany because they need the storage because of the wind generation issue that they're having, okay? And I don't poo-poo any renewable energy. Source power, I don't care if it's whatever it is, it's important because we're short. So from an international perspective, the CAGR, the compounded annual growth rate for the PSH pump storage hydro facility in global, from a global perspective, is at 13 to 14%. From a businessman's perspective, that's good. In the US, it's down around 5%. And I believe it's because of the regulatory constraints to unlock the guardian of the grid. That's what pump storage hydro is called, the guardian of the grid. There's been many articles written about that. I didn't invent that. So, but it's important, right? So from a global perspective, everything's going on. Oh, by the way, we have another, can I tell them about that other one that we have, Mark? Yeah, I can, right? Patents pending. So we have something that doesn't obstruct rivers, right? Fish can swim up and down the river and you can still generate power. That's a big deal. Because the environmental saving of fish and aquatic animals is absolutely critical. I mentioned before, we're teamed with Merck Animal Health and some other people on those types of projects. But we're not going to do a fish recreation water resource management way. I don't call it a fish way, and I don't call it a fish ladder. They can all be done at the same time, if done effectively, not as an afterthought. So if you're going to do it right. Or don't do it at all and avoid it and go somewhere else. But it is absolutely critical. Anyway, that's it.
Okay, thank you, Chris, on that. Maybe Nicola, just following up on that, if you have some thoughts from the materials side about sustainability of the materials themselves that are used in Cleantech, and also sometimes you have materials that are very scarce or that come only from one place in the world. Maybe just tell us a little bit about how that comes into your research when you're thinking about the materials.
Yeah, indeed. There's a lot, of course, of question about batteries, about lithium-ion batteries, about the availabilities, right, of lithium, cobalt, nickel, and that are in certain region of the world. So there's, of course, some limitations first. It's one point, like if you want to scale it up to sometimes the scales of pump hydro might be difficult in some cases, but there's also some other aspect of it, like the mining of it, that has an impact environmentally. So let's say it's water, but also just in CO2 emissions. So basically somewhere if we are trying to just withdraw CO2 by using solar and wind, we need to have something that's sustainable into that regard. So in the material side, there's a lot of, in the batteries, for example, a lot of new chemistries that are studied, and sodium-ion batteries, for example, or many others. So that's one way to try to do things like less, to have like a sustainable way of having these materials run. For us, that's the side we took, and is the side of using carbons. Carbons is widely available. One aspect we are looking at, and our other panelists that could not come also, I think, is working on this aspect, is to use biomass. Like if you use biomass and you are doing biochars, you can basically store CO2 through the plants and carbonize them. And so basically, it's used as a carbon dioxide removal technology. So basically, yeah, you grow plants, you capture CO2, you carbonize them, and that's one of our plans, for example, to introduce into our systems. You can make highly conductive carbons this way, and that would be one way also to, because if we introduce cement and concrete, concrete is 33 billion ton a year that's produced. So we will never make all of it, of course, as capacities. But if you could inject a lot of these biochars that are basically sink for carbon into that could be also a good way to have, let's say, sustainable carbon dioxide removal solutions.
Okay, thank you. Coming back to the level of running a business, Michael, maybe can you briefly tell us about your thoughts on using IP to protect your technology?
Before I do that, I want to follow up with Chris's thought about global energy storage. Do you know who invented energy storage in a large scale? The Swiss. 1880, they dammed up the river Limmat and mechanically pumped water to the top of a hill and let it down in the dry summer months so that they can keep their industry running. 10 years later, after Tesla invented the motor, the three-phase motor, they decided to electrify it, so they turned it into an electric operation. But I wrote about this one energy storage project in Switzerland in my book, and I had to go see it. So a couple of years ago, I went up to the top of this reservoir, 6,000 feet up, and I stood on the precipice of the dam, and I looked down over 4 terawatt hours worth of energy storage. 400 million cubic meters of water, 5,000 feet above their dam, above their machinery. So that's a lot of power.
A serious head.
A serious head, and a lot of energy. Unfortunately, it had a really low discharge rate of about 2,000 hours, so couldn't use it for our purposes here in the United States. But if you ever get a chance, go see one of those beautiful sites, as Chris had mentioned. So the value, the importance of IP in our company, it's the foundation of our competitive edge. In our business, margins are slim, business is cutthroat. We need that little edge. Now, we can maintain that edge by constantly inventing, and by definition, everybody else will be following, or we can patent and protect those ideas. And then we can wait, then our competitors will have to wait 17 years, pay us royalties, or think of clever and expensive workarounds to actually do the same thing. IP can help us in, it bolsters our image. We can proudly say, hey, we have these patents, right? And it bolsters our image in the marketplace. It can help us in the defense of a negotiated use of other people's IPs. At AESI, we upturn the apple cart all the time. You saw our Parallel Before series. That's kind of strange and innovative. We have the passive and inherent fire protection. That is something new in our industry. We have the 6-hour installation. That's also pretty innovative. And then our 5 nines of reliability for data centers levels. Those things are all the importance of IP in our business.
Great, great, thank you. And Nicola,
Add something just on that, because I hear from a company's perspective already, but for us, for example, IP is extremely important when we are starting or trying to start our startups, because for one point, but probably now it's not at your level now at this time, but for raising money. For raising money, having IP is critical, absolutely critical. So now we have a few patents and we can really discuss with people behind that, because without that, finding investors is way harder. Just wanted to add that.
Yeah, thank you. Yeah, Christopher.
Ditto.
All right, thank you. Well, so I think with that, we're done with the moderated part of the presentation, and I wanted to open it up to questions. So does anybody, we also have an online audience. Does anybody here in the room have a question? Okay, gentleman back there.
How will the carbonated, well, the carbonized, I guess, cement fare with an a lightning strike?
Okay, so the question was, how will carbonized cement fare with a lightning strike?
Yes, that's for sure a question we have very regularly. Indeed, it's kind of, so how we are looking at it now and how we are developing it at a larger scale is for foundations, mainly in the houses. So basically, one thing is, it's a supercapacitor. So now it will be in an enclosed chamber. It will always be insulated, because if you have an electrolyte in there, and especially for safety questions, we are working with water-based electrolytes. So you need an enclosure. So it will always be insulated from the outside and not directly naked concrete out there. It will not be possible. And yeah, we worked on other types also of electrolyte, not to have to enclose it, but then come some other issues, because we want it to be, it's a construction material, you want it to be almost infinite. You don't want at some point to have to replace a part. So working with this aqueous electrolyte is great for cyclability. So for now, it will be an enclosed system.
Hey, one comment. So we talked about hybrid approach, right? So there's need for everybody. So think out of the box. Floating photovoltaics on an upper reservoir, collecting solar, plugged into a battery storage farm that then can store the power and help with the efficiency of being able to pump uphill. Maybe explosive charges. I know it sounds strange, but something that moves water quicker uphill. Right? Those are some of the things that we're very, very interested in. Obviously, water stop, when you take gigantic Legos and put them together, they can't leak. Right? So how are we coming up with, when you talk about your technology, I'm thinking smart net over the top, right? That you can power up by, can you use light? Can you use laser? Potentially. There was a company called Ytricity, I think that came out of MIT a while ago, that was doing that, like recharging, right, while it was in the air. To me, that stuff's cool. I am a laser range safety officer, so I got to be careful, though. Anyway, hybrid approaches, hybrid thought, and then the acceptance from decision makers to listen to the technology brilliance and adopt. That's where there's always been a roadblock. We're going to do it the same way we did it because we did it 40 years ago like that. It's not 40 years ago. It's a clear present danger. Change your mindset and adopt novel, new methods and means.
All right, thank you. Other questions from the audience?
And you guys are shy.
Okay, we have one back there, Deirdre.
I do biotechnology. I was interested in the potential implications for assisting underdeveloping and developing countries like portions of Africa, with the implications of your technologies and how you could help.
Okay, so I'll just repeat the question. Interested in how your technology can help with underdeveloped regions of the world.
As a former Booz Allen Hamilton consultant, where I learned very early on, right, the State Department, USAID, and stuff like that with what's going on right now, let's not comment about that. The answer is yes. Bill had me take a look at it. The issue I ran into was there were other people there conducting. If you look at who's doing the water power, dams down there, there's other people there. So it's not a matter of not trying and not thinking about it, because precast could go in and do things rapidly, right? And enable villages that haven't had power. I will tell you this, though, our neighbor to the north, if you go further north, one thing, big advantage, precast, right? If you've never poured cement on a patio or anything, and one day it's 30 degrees and the next day it's 60 degrees, that's a bad pour. Precast is poured at 70 degrees, controlled environment, and it's perfect. You don't believe me? You hear the guy on Shea on the radio as you're driving in, Shea Precasters, right? That's Greg. I met Greg. And he looks like the concrete man, right? When I toured their yard, I went and I kind of drifted off by myself because that's the way I am. And I'm like rubbing my hand on these modules that had came out and cured after going in the forms. And I didn't feel cement. I felt granite. All right? No cavities, no cracks, no bad pieces, nothing. No crappy cement that sat in the truck too long before you poured it. I'm not poo-pooing the concrete industry and cast in place. But doing it in a controlled environment lowers the risk, makes the product better.
Go ahead.
So I volunteer for an organization called IEEE Smart Village. And one of the things that they try to do is bring power to the villages, and they target mostly 500 million people in Africa who have no access to power whatsoever. So kids can't read at nighttime, people are still cooking over gas stoves, and indoor pollution, whatnot. And so what their goal is, they bring solar panels to a village or a house, and then they have batteries that are coupled to the solar panels, and it allows them to charge the batteries in the day, and at nighttime use the electricity for refrigeration, for their lighting, for cooking, whatever. And so that's the thing that they do, village by village, and they also bring education. That's why they call themselves Smart Village. But the problem with that traditionally has been lead-acid batteries. So these poor villagers were given this solar panel and some banks of car batteries that went dead in about 2 years. It's not meant for that application. Well, along came Yet-Ming Chang from MIT with this nanophosphate battery that can cycle thousands and thousands of times. Suddenly, lithium-ion became a viable alternative for this very application because the thing could last 20 years. And before that, laptops that lasted 500 cycles was fine because you threw away your old laptop and you went on to a new one. But Yet-Ming Chang made this thing that could cycle thousands of times, and now suddenly it could be used for the grid. So hence, that's why A123 started that battery, the grid business, because for the first time ever, lithium-ion could be used for the grid, and that's a perfect application for that one. Only thing is hot temperatures. You got to put it in a nice cool place in Africa. Batteries are like people. They like to be cool. They don't like to be too hot. And they will degrade if you put them under abusive conditions. So is our products doing that right now? No. Do they have the capability soon in another evolution of our products? Yes, and I would be glad to do that.
Thanks. Yeah, totally. We have the same ideas. We have been working with a group in Senegal, actually, for this type of ideas. We are working with supercapacitors, so for the range of temperatures, it's easier. We have lower storage time. So basically, the idea we were discussing is when there's loss of electricity for shorter time, to have a backup behind that with an easy solution. And cycle life is huge, so it's almost an infinite. Hundreds of thousands of cycles, up to millions, actually, with some losses, of course, at some point, but yeah. So yeah, these are things we have been exploring too with this type of technology, but nothing, again, not ready or not in place, but it could potentially. I think any form of energy storage would be helpful in these situations.
Cold weather regions too, right? Alaska and northern Canada. Folks are burning dirty stuff to stay warm. And the construction timelines certainly are not, a 3-month open window to do heavy civil construction to build a dam or structure or something like that to generate power. It's just not in the cards. That's where precast comes in, and you can rapidly build in cold weather environments with good product. Because there are certain heats and temperatures. While I was coming in, I was Googling, and I've been there, Abu Dhabi and Dubai, Bahrain, Kuwait, I've been Kingdom of Saudi Arabia. The temperatures in the summer, I think the first time I was over in Bahrain, it was 120. And I wasn't sweating because it's like dry heat. Yeah, right. It was hot. And concrete loses its properties of a good pour at 120 degrees. Sometimes you can't even do it. So you're kind of reliant on your environment. But for austere locations and folks that need help, yep, we can do it. There is the supply chain piece. That's always a big thing. You need sand, you need cement. We're also working with MIT. Thank you. Eco Materials. So it's a company that started out of MIT, John Preston. Some of you may know John. And what we were looking at was using volcanic and fly ash, clean fly ash, to limit CO2 emission of concrete. Around the world, concrete is responsible between 9 and 10% of the CO2 emissions globally. So we need to get that under control. And by utilizing advanced materials, you can limit the CO2 emission coming out.
Yeah, I can only back up this. We have been also, I acted as a CTO of a company of concrete, and we basically started working with precast because to control every form of a quality of a final product is, of course, way easier.
Can't wait to get with you after.
We'll do that for sure.
All right, thank you. Do we have any other questions from the audience?
Yeah, I just, since you're talking about applications in Africa, I wonder if there's opportunity for more small-scale applications in the U.S., and especially in rural areas where power transmission is costly and inefficient, to pair with things that may be more abundant, like wind power, solar, that sort of thing.
Yeah, believe it or not, a huge number of people in the United States don't have access to any electricity. And so we've been working with several tribal nations to install some of our systems in community centers to run their communities and to provide power for the people for charging their batteries or phones, or providing retail services and cold beverages and whatever. So, and especially the emergency services of these communities. And it gets really hot, people can come and hang out in the cool weather. And that's that we've been quoting and working with several applications for that very purpose.
Most definitely. So, lot to share. Low profile model. Let's see, I wrote a white paper and submitted it to the Department of Energy, Water Power Technologies Office. It was called, I'm not the first person to think about it, low profile modular pump storage hydro, small scale. So we have a very significant partner that builds precast, prefab tanks. I can't disclose here, but I certainly will later. Please follow up. 5 million up to 60 million gallon tanks. I did all the pricing for those. That's on the pump storage side. We also installed our company, because we did the French dam, and then we did a micro turbine setup and installed it in 2 hours at 20 to 25 kilowatts. That's enough to power 3 homes along the Hudson River at an undisclosed location in New York. The problem with that is there's no money for I shouldn't say that. There's not enough return on investment for turbine manufacturers to get back into the micro turbine business. Personally, I wanted to put it as a GSA product, throw a couple turbines in it, and put it out there and mass produce it, and start another company and start banging away at it. Because then, if you have viable water source, which this person did, Everything in New York is kills. It's all called saw kill. It's all the water that comes running down to the Hudson, right? And that's where we did the installation. Crazy. I was there. 5 modular pieces came on a truck, and 2 hours later, they were installed and linkaged. And then we waited for the turbine manufacturer to come with the turbine, right? So yes is the answer. Microturbines there were companies that were doing them before. Toshiba actually was doing some work out of Japan. And there were other people that were doing that. I think if it was mass produced and you could do volume, then I think it might be viable. It would be something I would look at. Because when you can do 20 to 25 kilowatts, it doesn't seem like much, but actually it's a pretty good amount of electricity, especially if you get 365, it's flowing and keep giving you that energy.
Yeah, on our side, I think we might be a bit early. We are in a research stage on this, so we didn't really look at this in here. We are also looking at generally lower timescales of storage, so a few minutes. So we have been a lot of talks with data centers, people who need really to regulate their loads, or at least regulation on the grid on this type. So maybe we have a bit less insight on that side.
I can share drawings too, right? We got all complicated and got whirly lines, and we made all this extravagant stuff in our models. No. Simple, easy to mass produce. Don't have like lots of cuts because you need a form to put the concrete in to be able to have it cure in the form. So they're very, very simple, easily reproduced, easily placed, dowels, guides, everything. So that's just one thing I wanted to mention. We can do any shape, any surface too. Facing, you can do facing with precast in the mold. If you want it to look like that wall, that door, that ceiling, brick, marble, whatever you want it to look like. Look old, look new, which attacks the aesthetics. We were up in Vermont looking at some areas there where the concern was aesthetics. And people, they don't want this gigantic gray thing sitting in my backyard. I want beautiful. Well, that's not it. Just do it in facing. So when you pour the concrete in, you have your facing stuff in the bottom.
All right. Great. Thank you. Anybody else? Any other questions from the audience? One more back there.
Hi, I'm Roxana. Thank you so much. Really appreciate this panel. I'm a student at Yale in energy, and I love all of this. I'm curious. I actually have 2 questions, but I'll just ask one. I'm curious, as we're adding more batteries, we're complicating the grid in some capacity. And so what are other ways in which the infrastructure needs to be improved so that we can better manage the transmission or how the power actually flows on the grid so that those efficiency gains are not lost in congestion?
Big question. And yes, it is complicated. It is the largest machine in the world, this power grid of the United States. And there's tens of thousands of things connected to it, all working together. And one of the things I was thinking of is as you were asking that question, is if you're centralized energy storage or generation in one place, you have to get it to all the corners of the grid, and a lot of that energy is lost along the way. If you put energy storage where there's the most activity up and down, either the load is up and down or the generation is up and down, you reduce the amount of transfer of energy back and forth. You reduce the distance that it has to go. So distributed energy storage that's pervasive in every household, connected to every car, vehicle to grid, all of those things. If you can distribute energy storage or generation, like generation on every house, every building, then you reduce the reliance of having to transport it physically, and then you can make that transport a lot more efficient. So those are the things that I can think of. You can also think of things like smart loads. Like, for example, if I'm if I'm like a hydrolyzer or I'm a thermal heat generator or a cooling device, and I have a large amount of energy that I need to use, well, maybe I can time it with available energy available that might be near me. So if I know that my solar is going strong near me, I might time it with that. Or if I know that some other generator that's running in my vicinity. So as the grid gets smarter, it's not just more wires, but it's acting in a better timely manner. So that's what the smart grid is supposed to be about, and I think we're moving toward that direction.
Standardization. We meet with a lot of power companies, little power companies, big power companies, a lot of different people, and they're constantly in a battle. It's almost like they're trading power at certain costs that is better for them, is not good for them, it's good for them. Standardization. I know that sounds like a walk away, but I kind of don't think we have that. We have people competing, and they do good if they save some money here or there, and someone else suffers. So I think from a federal perspective, the standardized grid, and the other one is utilize AI for optimization of transfer. You know, find those leaks, right? Find those areas, find those cracks, because in this world, I went to Annapolis, right? So I'm ashamed to say, but I felt bad for Hadley Falls, which is where West Point's located, right? They had some bad floods that ripped like an entire road out, and some good property damage and stuff like that. We have up in Vermont, I spoke to Ben Green, who's the dam safety officer. He goes, we almost lost Waterbury. Ooh, that's not good. And we also had 4 dams that just completely washed away. I'm the guy that calls New York on Long Island to Stony Brook and says, yeah, we can build it for $5 million. We could put a new dam in place for you. But there's so much politics and stuff that they're going to spend $40 million on a project. Remember, I told you a French dam, right? Bill French did the Fast 14. We can come in there with a solution. I know it doesn't look at all aspects of labor and manpower and union and everything like that, but if you need it quick, you should be utilizing the best access at the best price. So give us a shot. That's what I'm just saying to these people. Optimization.
Yeah, indeed. I think it's a very complex problem through the grid, because it's already very complex in itself. Now you're introducing renewables with energy storage in every places, individual storage at the places, and you need to balance all of that. It becomes exponentially more complex as more renewables are entering the game. So this is, yeah, there's a big challenge in energy storage. There's a big challenge, I think, in managing the grids, and AI tools booming, actually, I think, in this area.
So I need 100 years of hydro. I'm building a digital twin model. I got an 86-inch model. I'm building a cave, right? I've got a girl, I hired her while she was speaking at Northfield Mountain in front of 500 people. 500 people there, I stood up and I said, that's the best presentation I've seen all day. I'm hiring you. Her name is Letitia Giulio. She's amazing, right? #1 in her class. And MIT, don't get mad, and other universities, I saw Northeastern and some other folks. She won the Department of Energy Water Power Technologies Award, #1, from Endicott College. Interesting, right? Her project of using a mill up in Lawrence, Massachusetts, working with, Archimedes screw turbines, won first place out of 40 colleges and universities throughout the country, and they got funded. And they finished in first place. After the girl presented, I'm like, she's amazing. I didn't even know how good she was. And so she is the owner of all the models that we have. Every single thing I've talked about, dams, micro, run of river, fish passage, aquatic, pump storage, hydro, it's already modeled. We already have conceptual models built on all of that stuff. And now I want to use model-based systems engineering trade spaces to get the regulatory people to be able to prove stuff rather than having to get it wet and figure it out that way. You can use that. I use that at Raytheon. We use that on planes in the DoD for years.
Was there a second part of that question, or was that already the?
There's actually a second part.
Okay.
I'd love to hear, so we've been talking a lot about the production side of energy and also, I mean, storage, right? But I'm curious on the consumption side, how viable do you think it would be to do flexible pricing, unlike in the US, but like in a lot of places in Europe, to not have fixed rates, but rather to actually see what your prices are going to be in a day in advance and or have a threshold you're paying to kind of use up to that threshold, but then anything above that, you're paying a lot more. And so what are some ways in which maybe through policy we can change consumer behaviors?
Yeah, and this was something, this is yet another talk that we could have. We're talking more about policy and the sort of the social side. But anybody want to take that one? Michael?
I'll answer anything. It doesn't matter. Great.
That actually exists down in Texas. I know of stories of people who've been checking their phones regularly and make sure that their air conditionings are not going to turn on when the cost of energy spikes. But you're right, it's not everywhere, and it needs to be everywhere if you want to change people's behavior. If appliances were plugged into that same kind of thing, and I know they are in some utilities, I have, in some of my appliances, the ability to connect to some utilities, but not mine, unfortunately, to power on when the rates are lower. And so that would make me a smarter consumer. Right now, I just come home, plug in my car, and turn on the air conditioning whenever. I don't care about what time. But if I had time of day, I would change my behavior. I might. Not everyone would, but it would move the needle a little bit, absolutely. And I'd love to see it. Really would.
Actually, I'm living in Europe now, and we have hours. We have certain hours where electricity is less expensive, middle of the night, where people are not using. So we generally do our washing machine at that time. It's like planned like this, and maybe would be interesting to have it like sticking to the real price would be great. For now, it's not what it is. Now we have slots of certain times where it's generally the case, where it's less expensive, so this is what's happening. And many, many people, I would say, do it. But having something, let's say, sticking to the real price would be great.
All right, great. Well, thank you so much. And I'd like to thank our speakers here. Maybe we could all give a round of applause for the speakers. Thank you.
That's very nice. Thank you very much.